So, hello aspirants. In today's video, we will be discussing a brief overview of the overall concept of enzyme kinetics, focusing majorly on graphical representations and mathematical formulations that is very common in case of CSIR as well as DBT-BET and even GET Excel and biotechnology as well. So, let's start. So, before entering into the advanced features, the advanced aspects, first we have to say we need to know what is a transition state. Suppose an enzyme, let's see, suppose an enzyme is binding with its substrate and eventually it is forming enzyme substrate complex, and from ES they will provide enzyme as product. This is the overall approach. All of you must be aware of it. So let's see. Before application of any kind of enzyme into any kind of reaction, let's focus on this graph. So this is the substrate in its ground state. Whenever this substrate is converting into product, certain amount of energy is applied into the substrate that is helping it convert into the product. So the applied energy upon the substrate convert into the product is this. We are stating it as free energy. Now this free energy that is being applied on substrate is helping that substrate to convert it into product. As simple as that. Now the fact is, so delta G, that means Gibbs free energy, the delta G for the reaction that is helping substrate to convert into product is negative. Negative delta G, we all know delta G negative. That means reaction is thermodynamically favorable. All of you must be aware of it. Here also delta G from substrate to product. So this transition from S to P, this is the positive side, and by converting into product, the energy transition has first elevated and then down regulated. So the delta G over here is negative. So this kind of energy or free energy that is helping the conversion of substrate in product is thermodynamically favorable. That means applied energy is helping the conversion. So delta G degree for substrate to product is negative. From this, we have came across a term called activation energy. Activation energy is stated as a barrier between substrate and product. It's a barrier between the substrate and the product. So this activation energy is required for this kind of conversion from substrate to product. Now, what is transition state? Transition state means suppose a substrate is inactive and we are trying to convert it into a product. So that substrate has to reach to a state from where it will be converted into product. Suppose this simple reaction E plus S. So ES is stated as the transition state. This transition state is furthermore helping that substrate convert into product. This is an enzymatically catalyzed reaction. Even if it is not, there is not any kind of application of enzyme, but still substrate is converting into product. আমি বলছি যে যদি সাবস্ট্রেটের সাথে এনজাইম বাউন্ড স্টেটে থাকে, ইটস ওয়েল এন্ড গুড। But যদি সাবস্ট্রেটের সাথে এনজাইম ইভেন বাউন্ড নাও থাকে, then also what will happen, that substrate will be converted to product by application of energy. আর এই যে স্টেটে গিয়ে that substrate is getting converted into product, that is called the transition state for the substrate. So this is the basic concept of any kind of reaction where a substrate is converting into product. Here we haven't shown the application of enzyme yet. Here we haven't shown till now application of any kind of enzyme yet. Now let's see. Whenever enzyme comes into action, suppose reactant is converted into product. This is the transition state, as I have mentioned, and energy is applied that is helping the conversion of reactant into product. Whenever the reactant is devoid of any catalysis, whenever the reactant is devoid of any enzyme, তখন কি হচ্ছে? The transition state, in order to reach the transition state, that means suppose a substrate that is getting converted into its transition state. From transition state, it will form the product. So the applied energy or the free energy, applied energy for this kind of conversion is high. The applied energy for this kind of conversion is high. Whereas if this substrate is getting converted into product via transition state with the help of any kind of catalyzing reagent, then the applied energy will be low. I'm repeating myself. Suppose a substrate is converting into product via a transition state. So if this substrate is converting into product, then there must be certain amount of energy that is applied to it. That applied energy without any kind of catalyzing reagent is high. But if that substrate is converted into product by application of a catalyzing reagent, then in order to reach the transition state, I'm repeating myself, in order to reach transition state for the substrate, applied free energy is low. So this graph states the same thing. This is our reactant, this is our product. Now this reactant is converted into product without any kind of catalyzing reagent. See, the applied free energy is high. Whereas whenever any kind of catalyzing reagent is added to the reaction, the applied free energy is low. As simple as that. Whenever enzyme, coming to this graph, whenever enzyme is applied, this is our substrate converted into product. This is our substrate converted into product. So this substrate is initially, without using any kind of enzyme, reaching its transition state by application of energy. Now this transition state, in order to reach the transition state, applied free energy is pretty high. Now enzyme is applied into the reaction, just like as I have stated, E plus S, ES. So whenever this ES, see, the applied transition state energy, applied energy is comparatively lower, is significantly lower. The applied transition energy, the applied energy is significantly low compared to that when substrate is getting converted into product without any enzyme. So with enzyme, energy is low. Without enzyme, energy is high. Applied energy. So this is how the overall process of conversion from a substrate to product is taking place. From substrate to product is taking place with the application and without the application of enzyme. With application of enzyme, free energy application is low. Without enzyme, free energy application is high. We just need to remember this. These are pretty basic concepts. Uh, yeah. Another concept. Initially, it was thought. Suppose this is our enzyme and this is our substrate. So whenever enzyme is binding with its substrate, this kind of binding is promoting ES into E plus E. Initially, it is kind of this. But later on, it is being observed that enzyme in general, the binding site for its substrate. As you can see over here, the enzyme is binding with its substrate. Here, according to the new concept, enzyme while binding with the substrate, it cannot recognize the substrate in its inactive state. It cannot recognize the substrate in its inactive state. Rather, the substrate is getting into its transition state. Then only the enzyme will be able to recognize that substrate. Initial concept, enzyme binding with the substrate, it shows binding affinity. Later on, enzyme binding with the substrate cannot bind with the substrate. Whenever that substrate is reaching its transition state, then only this enzyme substrate complex formation will take place. And that will eventually form enzyme plus product. So this is the overall approach according to new concept. An enzyme with a pocket complementary to the reactions transition state. Very, very important. This is the advanced concept. And this is the primitive concept. That enzyme is perfectly complementary to the substrate. So all of you must pay attention whatever the statement is provided in the exam. I have previously mentioned this kind of thing. Okay, so these are the basic general characteristics of any kind of active site present within an enzyme. I have introduced this slide so that anyone who is opting for exams other than CSIR-NET, like DBT-BET or GET Excel, they can even find in short questions this kind of statements. In CSIR-NET, you won't be able to receive these kinds of questions. Mostly, the question occurs from graphical representations or mathematical formulations. But other than CSIR-NET, you will find something like this also. The active site is a 3D cleft or crevice. Water is usually excluded. Water is excluded. Very, very important point. Water is excluded unless it is a reactant. In any kind of enzyme substrate complex, water should be excluded out until and unless it is a reactant. Substrate binds with the enzyme by multiple weak interaction. Everyone must pay attention to this statement. Multiple weak interactions, specifically electrostatic, hydrogen bond, and hydrophobic interactions. Electrostatic, hydrogen bond, and hydrophobic interactions. Covalent interactions are very, very rare when it comes to enzyme substrate complex formation. In most of the cases, weak interaction takes place. Fourth, specificity of binding depends on precise spatial arrangement of the atoms. It is precise spatial arrangement. Suppose there's an example over here. There's a histidine residue. There's a histidine residue. Histidine position 119, 96, and 94. And there is Zn plus. H2 is there. So the binding, this is an example of carbonic anhydride base. So this kind of thing, this kind of arrangement of certain amino acids or molecules are extremely efficient for binding that product. So first point, which is important, water is usually excluded first. Secondly, mostly they are weak interactions like electrostatic, hydrogen bond, hydrophobic interactions. Second important point. Okay. For part B, this segment, extremely important. Which metal ions it corresponds with which of the enzyme? Very, very important. Specifically Zn plus. We all are aware that it is associated with carbonic anhydride base, but it is also associated with carboxypeptidase as well. Mg plus, EcoR5, Mg plus, mostly we know hexokinase. Molybdenum, nitrate reductase. Selenium, glutathione peroxidase. Women plus, superoxide dismutase. Every metal ion associated with enzyme. This kind of questions mainly will appear in terms of mismatches. For coenzyme, definitely biotin, very important. Pyridoxal phosphate, NADH, very important. These are all informative aspects. Nothing to conceptualize about it. For DBT-BET, this table, very important. What are the classes of enzyme and types of reaction that it catalyzes? Specifically for GET-XL and DBT-BET. Not so. This is another aspect that can be taken under consideration. EC2711. What does this mean? Enzyme commission. It denotes the class name. That means, as I have stated previously about the classes of enzyme, it states about that. 7, it denotes the subclass. That means whether this kind of transfer is 2, it is a class. 7, it is a subclass. Means whether it's a phosphotransferase or something. 0.1, it denotes hydroxyl group is there, and that 0.1, it denotes the D-glucose. So these are the things that should be. I haven't seen this kind of question previously, but there might be a possibility where enzyme commission is provided and they can ask you about what stands for what. Now, catalytic efficiency, as we all know, what does catalytic efficiency mean? Let's see, an enzyme is getting converted. Enzyme is converting a substrate into product. So the fact is, whenever the product is formed, as I have stated previously, that there lies the conversion from substrate to product by means of a transition state. So enzyme helps the substrate to reach to the transition state with least amount of activation energy. Whereas if the substrate is getting converted into product without the utilization of any enzyme, then this conversion will require huge amount of activation energy. So from this aspect, we can state that least activation energy, that means more catalytic efficiency, and more activation energy is least catalytic efficiency. So they are inversely proportional to each other. What kind of catalysis normally occurs is mentioned over here. Acid-base catalysis is very frequent. Covalent catalysis is very rare, as I have stated previously. And third one is the metal ion catalysis. I have stated a few examples. If you wish to receive the PDF, then let me know in the comment section. I will deliver. Or rather, I can even attach my Telegram group link where you can join the group, and all the notes regarding the classes will be shared over there. Now, starting with the enzyme kinetics. We all know the basics of it. E plus S converting into ES. From ES, we are getting E plus P. So for E plus S, for this step, the rate constant, suppose it's K1. And from ES, again getting reconverted into E plus S, it is K minus 1. Similarly, for E plus P, we are stating K2. Now, if in general, what happens? In general, in a normal scenario, initially the substrate concentration is high. But as the enzyme substrate complex is getting formed and that substrate is getting converted into product, the substrate concentration will be lowered and product concentration will increase. So this is the normal scenario. That is why substrate concentration cannot remain constant for a prolonged period of time. This is not possible. This is stated over here. Effect of substrate concentration on the initial velocity. Substrate concentration is a variable parameter since it is constantly being converted into product. But if substrate concentration is much greater than, if substrate concentration is much greater than enzyme concentration, if substrate concentration is much greater than enzyme concentration, and we are plotting V naught against substrate, we are plotting V naught against substrate concentration, then it gives us a hyperbolic curve. It gives us a hyperbolic curve. And what is Km? Km should be considered as substrate concentration when V naught equals to Vmax by 2. That means, according to the typical Michaelis-Menten equation, what we all know, V naught equals to Vmax into substrate concentration by substrate concentration plus Km. Let's plot V equals to Vmax by 2. Then we will receive something like this. So this is the typical example of a enzyme substrate reaction. When substrate is much greater than enzyme concentration, we will receive a hyperbolic curve. And Vmax is the ultimate velocity. What is pre-steady state? Initially, from this graph, you can see initially the substrate concentration is high. But as the substrate concentration, as the enzymatic reaction is going on, the substrate concentration is getting lowered. Similarly, product concentration is getting higher. So, for a certain period of time, probably microseconds, what will happen when an enzyme is first mixed with a large excess of its substrate? Initially, substrate concentration is high, and that high substrate is coming in contact with the enzyme within the solution. There is an initial period during which the concentration of ES complex builds up. The concentration of ES complex build up. I mean, ES complex will be high for a certain period of time. For a certain period of time, it will be built up. This state, this state where the enzyme substrate concentration is getting higher because of initial high concentration of S. During this phase, when the enzyme substrate concentration is higher because of increased concentration of substrate within the solution, that is called the pre-steady state. Later on, this ES will be at equilibrium. Later on, the ES concentration will be at equilibrium. That means substrate concentration is now gradually getting decreased and ES concentration is formed. That ES concentration is converting that substrate into product. That ES is now converting ES into product. So ES, then what it forms? E plus P. So product concentration is getting increased and ES concentration is maintained at a steady state. ES concentration is being maintained at a steady state. This is called steady state kinetics. This is pre-steady state and this is called steady state kinetics. For Michaelis-Menten equation, we will definitely use this reaction. Why not this? Because there lies a problem. Initially, what happens? Initially, ES is getting converted into E plus P. But E plus P is not getting reconverted into ES. E plus P is not getting reconverted into ES. So that's a unidirectional reaction in the beginning. And for the simplification of the overall Michaelis-Menten equation establishment, we will be considering this equation and deriving the rest of it. Another thing we must understand from this is, as you can see, E plus S, ES from there E plus P. For the first step, K1 is a rate constant and K2 is the rate constant for the next step. So, K2 in this reaction can be stated as the rate limiting step. That means that will help in the conversion of substrate into product. That is the determining step. That is the determining step. So rate limiting step is nothing but the determining step. And over here, K2 can also be stated as Kcat. K2 can also be stated as Kcat. So if that kind of a thing is occurring, then If that kind of a thing is occurring, then we can easily state V equals to, they have stated regarding this, V equals to K3 into ES. V naught, we all know, equals to Vmax into substrate concentration by substrate concentration plus Km. This is the overall reaction. Suppose we are considering this. That means E plus S, K1, ES getting converted into E plus P. So ES is getting converted into P. So the initial velocity is the breakdown of ES. The initial velocity should be based upon the breakdown of ES into E plus P. So that's why the initial velocity V naught equals to K3 into ES. K3 into ES. Now, so let's see. We have E plus S, ES. From there, we are getting E plus P. So this one is K1, this one is K minus 1, this one is K2, which is the rate limiting step. So we have established V naught equals to K2 into ES, as ES is getting converted into P. And what should be Vmax? Vmax equals to K2 into ET. Why ET? Because over here, ET is stated as total enzyme concentration within the reaction. Total enzyme concentration. So ET should be E plus ES. E means free enzyme, till now free enzyme, and ES should be enzyme bound to the substrate. So the total enzyme should be free enzyme, that is still not bound with the substrate, plus ES, that means total enzyme. So from this, the final velocity of a enzymatically catalyzed reaction should be K2 into ET. K2 into ET. Clear? And V naught equals to K2 into ES. These are very important aspects that should be taken in under consideration, as any kind of mathematical based questions can arise from these equations. Now, another important thing. Let's say a substrate A is getting converted into product B. As a result, this A, as it is getting converted into P, A will be dissociated and P will be formulated. A will be dissociated and P will be produced. So, V naught, or the initial velocity, can be minus dA by dt. DAY, because dA is getting dissociated, that is why minus, into by dt. So dA by dt can also be stated as dissociation constant K into A. This can also be the approach. See, A is getting converted into P. So A is getting dissociated, P is formulated. So velocity should be V naught equals to, as A is getting dissociated, then A by dt. At certain amount of time, dissociation of A equals to K into A. Why K into A? Because dissociation constant K. Now, if we consider this segment, let's see, dA by dt equals to K into A. Or if we use logarithm on both the sides, sorry, integration on both the sides, dA by dt equals to integration of K into dt. Or from this, we will finally get, and the limit should be A0 to A, from A0 to A, from initial to final, where A0 should be the initial concentration and A will be the final concentration after getting converted into product. This is how the overall process of integration works. After series of equations, what we will finally release, we will receive ln A equals to ln A naught minus kt, or A equals to A naught into e to the power minus kt. This can be the final reaction. As this overall reaction is a unimolecular reaction, we are stating it as first order kinetics. First order kinetics. Very, very important. So this is the final output. See over here, A to P. So V dA by dt K, we are integrating it and finally receiving what? A equals to, ln A equals to A naught into e to the power minus kt. Now A into e to the power kt can also be rewritten as ln A equals to ln A naught minus kt. And if we plot this in a graph, then what will be getting? On the y-axis ln A, on the x-axis T. The reversible format for straight line equation. And the slope over here is K. So this is the first order reaction kinetics. The first order reaction kinetics. Now suppose a certain kind of equation is provided where small a into a, capital B into B, something like this, and they are getting finally into, they're converting into product. So the overall order should be, the order of the reaction should be, we need to take these factors only. So A plus B plus C up to Z, that should be the overall order of the reaction. That is why it is stated for this reaction, it is a unimolecular reaction and that belongs to first order. That belongs to first order. So for first order, what we are getting? A equals to A naught into e to the power minus kt, or ln A equals to ln A naught minus kt. And if we plot this entire reaction over the graph, we will receive something like this. If someone is not aware of the integrating portion, then they can even recall this entire thing. Though I will must state that some mathematical formulations are needed for the proper conception regarding enzyme kinetics. It is essential. Second order reaction, I haven't seen any question, but still it is somehow related to first order reaction as well. Over here, 2A getting converted into P. As simple as that, as initially we have considered V equals to, as A is getting deduced, A is getting reduced. So dA by dt equals to, now it is converting into product. So dP by dt equals to Ka square. Now dA by dt equals to Ka square. This is basic mathematics. All of you must be aware of it. As V equals to dA by dt, and as it is a dissociation constant, then Ka square. So dA by dt equals to Ka square. Now dA by a square equals to K into dt. And integrating on both the sides, we will finally receive something like this. 1 by A naught, 1 by A equals to 1 by A naught plus KT. 1 by A equals to 1 by A naught plus KT. This is the second order reaction. This is the second order reaction. And after plotting it, we will receive something like this. So first order reaction, we have plotted against logarithm ln A equals to ln A naught minus KT. And over here, we have plotted something like this. Derivation is pretty simple. For over there, it's A converting into P. Over here, we are stating 2A getting converted into P. And rest of the thing is same. As A is getting converted into P, then dissociation of A, dA by dt, and dissociation constant Kd should be Kd into A square. Why square? Because two molecules of A is involved. That's why K square. Now plotting these two, we are finally getting this kind of an approach for second order. Now coming to our Michaelis-Menten equation. I have derived the entire thing. If someone is not willing to get into the details of it, he or she can definitely memorize or learn the output, the final output of it. That will be sufficient for solving the problems. But for conceptual approach, I must state one thing. You need to know, suppose E plus S, ES getting converted into E plus P. In any kind of reaction at equilibrium, rate of formation of ES should be equivalent to rate of breakdown of ES. So if the rate of formation of ES is K1 into ES, K1 into E into S, then rate of breakdown should be either ES into E plus S or ES into E plus P. So both the aspects should be considered when it comes to breakdown. Both the aspects should be taken. For formation, E plus S getting converted into ES. For breakdown, E plus S, ES is getting either converted into E plus P, one aspect. Second aspect, ES can reconvert into E plus S. So this is the overall approach when it comes to rate of breakdown. So overall rate of formation equals to rate of breakdown. And after deriving a series of equations, finally what we are getting, V naught equals to Vmax into substrate concentration by substrate concentration plus Km. This is what we are getting. Now, previously, we have encountered a few aspects, a few formulas. What are they? One thing we have understood is V naught equals to K2 into ES. This is first thing we have known. Second thing we have known, Vmax equals to K2 into ET. That means total enzyme concentration. Third thing, rate of formation of ES equals to rate of breakdown of ES. Third thing. Fourth, Km, Michaelis constant, equals to K minus 1 plus K2 by K1. Another important thing. Ks equals to K minus 1 K minus 1 by K1. These are the few things that should be remembered if someone is not aware of the overall process of derivation of Michaelis-Menten equation. Very, very important. So we have till now we have received Michaelis-Menten equation as a whole, first order and second order kinetics, their formulations, their graphical representations regarding enzyme. Next, we have discussed about steady state and pre-steady state kinetics. Then enzyme, when combining with the substrate, getting converted into ES from their E to P. So rate of formation is ES. Rate of breakdown is ES from either E plus S or E plus P. And Michaelis constant Km equals to K minus 1 plus K2. That means the rate limiting step divided by K1. And Ks equals to K minus 1 by K1. These are the few things that should be taken under consideration regarding mathematical calculations. And always focus on the graphs. Very, very important. Now, so if V naught, if V naught equals to Vmax, substrate constants again. Now, if Vmax is V equals to Vmax by 2, as I have stated in a graph previously regarding Michaelis-Menten kinetics, that when substrate concentration is much, much greater than enzyme concentration, and V naught, when substrate concentration is much, much greater than enzyme concentration and V naught equals to Vmax by 2, then substrate concentration should be Km. Then substrate concentration should be Km. That is the same thing mentioned in this graph. See, Vmax is the ultimate stage, V naught on the y-axis, Km on the x-axis, where Km equals to substrate concentration when V naught equals to Vmax by 2. I guess up to this point, every aspirant must be aware of this overall thing. What is the criteria that is also remembered? Substrate concentration has to be much substrate concentration has to be much greater than enzyme concentration. This is the criteria in order to receive this hyperbolic curve. So, this is how the overall Michaelis-Menten equation is being established. No need to go through the details of it. So, this is the final form. So, this is Michaelis-Menten equation for one substrate enzyme catalyzed reaction. One substrate enzyme catalyzed reaction. Very important. Statement of quantitative relationship between initial velocity and maximum velocity and initial substrate concentration. Yes, all related through Michaelis constant Km. Km has the unit of concentration. Km has the unit of concentration. At low substrate concentration, Km is much greater than substrate, and Michaelis-Menten equation M equals to Vmax into S by Km plus S. When substrate concentration, mind it, when substrate concentration is low, is much low than Km, then V naught equals to Vmax into substrate concentration plus S plus Km. Substrate concentration is very low, so we can state over here V is equal to Vmax into S by Km. So V exhibits a linear dependence on S. This point is very important. V exhibits a linear dependence on S. When substrate concentration is low, that means the graph should be linear. But when substrate concentration is low, we are getting something like this. The final output should be something like this. V equals to Vmax into substrate concentration by Km. So V, which is Y equals to Mx. Y is equal to Y equals to Mx. That means linear graph where V naught equals to Vmax into S by Km. So this is a linear graph, straight line graph. But whenever at high S, substrate concentration is high, whenever the substrate concentration is high, S is much greater than enzyme concentration. Then what is happening? Then V equals to Vmax into substrate by Km plus S. That means V equals to Vmax. This is consistent with plateau observed at high S. So whenever substrate concentration is low, what we are getting? V naught equals to Vmax into S by S plus Km. Now, as S is much less than Km, then S should be negligible. This S should be negligible. So in the denominator, we are considering V naught equals to Vmax into S by Km, which is Y is equal to Mx reaction. Linear. So the graph should be linear. Whenever substrate concentration is much greater than Km, substrate concentration is much greater than Km. So Km should be denominated, should be eliminated. Whenever substrate concentration is much greater than Km, so the equation is V naught equals to Vmax into substrate by S plus Km. Therefore, V naught equals to, as S is much greater than Km, so Km should be negligible, leaving S, so V equals to Vmax. So this is consistent with the plateau observed at high S. So this is kind of an approach. This kind of an approach is observed. This kind of an approach is observed when S is less than Km. And this kind of an approach is observed when S is much greater than Km. All of you must pay attention over here. This kind of an explanation is very interesting and very informative as well. So V naught equals to Vmax into substrate by Km. Why it is linear? Because we are following the typical straight line curves. Y is equal to Mx, where S is much less than Km. But whenever S is much greater than Km, then what is happening? V equals to Vmax into substrate by S plus Km, where S is much greater than Km, therefore Km is negligible. So we are eliminating S and S. So therefore V equals to Vmax. When V equals to Vmax, this should be the graph. So this is the ultimate form when S is much greater than Km. And this is the ultimate form when S is much less than Km. I hope it's clear now. And in between these two, what we are getting? This graph. When you are getting this kind of a graph, when V naught equals to Vmax by 2. Then S equals to Km. And if S is equals to Km, then we are getting something like this. I'm repeating myself. When substrate concentration is much less than Km, V equals to Vmax into by S plus Km. Therefore, V naught equals to Vmax, substrate concentration much less than Km. So S, we are eliminating this, so Km, or Y equals to Mx, typical linear graph. Condition 1. Condition 2. Substrate concentration is much greater than Km. So V naught equals to Vmax into S by S plus Km. As it's much greater than Km, so Km should be negligible. Therefore, leaving V naught equals to Vmax. And third but not the least condition, V naught equals to Vmax by 2 when substrate concentration equals to Km. So these are the three conditions. Condition 1, condition 2, condition 3. This shows hyperbolic graph. This shows linear graph. And this shows parallel to the axis. So this is the overall derivation of this equation. This is the overall derivation of this equation. Now, coming to Lineweaver-Burk plot. Oh, another thing I must state, I just forgot to mention. Previously, we have came across the term Km. Now, all of you must know that whenever the value of Km is high, that means an enzyme has least affinity towards substrate. When the Km value is high, then enzyme has least affinity towards substrate. Whenever the Km value is low, the enzyme has high affinity towards substrate. That means high Km, least affinity, least probability of forming product. Low Km, high affinity, maximum possibility of forming product. So I'm repeating myself. Km high, Km low. Km high, that means enzyme has least affinity towards substrate. As least affinity towards substrate, then the product formation should be least. Whereas Km low, that means enzyme has high affinity towards substrate. As high affinity is there, then maximum amount of product will be formed. So this is the overall correlation in between Km, enzyme, and substrate. This is very important. You can find varieties of questions regarding this in CSIR-NET as well as DBT-BET. So V equals to Vmax into substrate by S plus Km. Now the reciprocal plotting is 1 by V, that leaves with 1 by Vmax plus 1 by Km into 1 by S. You can also derive it if you wish to. This is pretty simple. So this 1 by V, 1 by Vmax and Km into 1 plus S, it corresponds with our y is equal to mx plus c reaction. And y is equal to mx plus c reaction, if we plot it over the graph, then on the y-axis, we are getting 1 by V. On the x-axis, we are getting 1 by S. And m, that means slope. The slope is Km by Vmax. Now, if someone is not aware of how to determine a slope, then we have to state the fact, we have to consider something like this. Let's say for x-axis intercept, y should be 0. Therefore, y is equal to mx plus c, or if y is equal to 0, then x into m is equal to minus c, or x is equal to minus c by m. Now, c over here, let's say c over here, 1 by Vmax. And m over here is Km by Vmax. So leaving us with 1 by Km. See, 1 by Km. This is what? This is our x-axis intercept minus 1 by Km. Similarly, y-axis intercept. That means x equals to 0. Y is equal to mx plus c. Therefore, y is equal to c. That means c over here, what is c? 1 by Vmax. So y-axis intercept is 1 by Vmax. So we have got our, on the x-axis we have 1 by V, on the y-axis, we have 1 by V, on the x-axis we have 1 by S. Our x-axis intercept is 1 by Km. How have we derived it? Like this. And on the y-axis intercept we have 1 by Vmax. This is how we have derived it. Now the slope is delta y by delta x. Therefore, over x in axis intercept we have received what? One by k over y we have received 1 by Vmax, and on the x we have received 1 by Km. So Km by 1, therefore coming to Km by Vmax. So this is how the slope is determined. M. So this is the basic calculation how we usually detect or determine the slopes. I think all of you are aware of it, but I must repeat myself. As we have initially Michaelis-Menten equation V equals to Vmax delta S. Now inverting it, we are getting Lineweaver-Burk plot, which is equivalent to y is equal to mx plus c. Now we are plotting y is equal to mx plus c against our graph, straight line graph, where y axis is 1 by v, x axis is 1 by s, and c is our 1 by vmax, and m is our slope km by vmax. Now, how we have determined this x axis intercept and y axis intercept? Let's see. When it comes to x axis intercept, then y should be 0. If y should be 0, then y is equal to mx plus c. When y 0, then m into x is equal to c, then x is equal to minus c by m. And if we plot it, then finally we are getting 1 by km. So our 1 by km is x-axis intercept. On the negative side, that means minus. Similarly, when we are plotting our x-axis, y-axis intercept means our x equals to 0. If x equals to 0, then mx is 0, then y is equal to c. That means 1 by vmax. So our y-axis intercept is 1 by vmax. Now slope should be y by x. Now we are plotting y, that means 1 by vmax, by x, that means 1 by km, finally getting km by vmax, which is our slope. This is how we are establishing this overall reaction. It's pretty simple, and all of you must be aware of it. So this is the Lineweaver-Burk reciprocal plot. So the double reciprocal plot presentation, also called the Lineweaver-Burk plot, has a great advantage: accurate determination of Vmax, which can also be approximated. No need to go to the details of it. Just focus on the graph, one. Secondly, about the slopes and the intercepts. These are the intercepts. Just focus on them and you will get the mathematical problems out of it. As simple as that. That will be, that will be sufficient. This is very important. Now, comparison. For this one, what should be the criteria? Substrate concentration when much greater than Km. Therefore, V naught equals to Vmax into S by S plus Km. As Km is negligible, therefore V naught equals to Vmax. So this is plotted over here. Vmax. This should be the ultimate form. Whenever S is equals to Km, that is when V naught equals to Vmax by 2. That is plotted over here. So finally, what we are receiving is a hyperbolic curve. Whereas in Lineweaver-Burk plots, we are inverting both the aspects. As a result, what we are receiving, the equation that I have previously mentioned, 1 by Vmax, where our x-axis should be 1 by S, y-axis should be 1 by V, our slope, as I have mentioned, and its derivation, Km by Vmax, and the y-axis intercept minus 1 by Km. And our x-axis our y-axis intercept 1 by Vmax, our x-axis intercept minus 1 by Km. This is how the overall Lineweaver-Burk plot is established, and this is the overall comparison. This is the overall comparison in between these two graphs, one with the inverted form and one with the normal form. One showing straight line curve, another showing hyperbolic curve under same conditions. Mhm. Just go through this statement. Halden relationship, it demonstrates that the kinetic parameters of a reversibly enzymatically catalyzed reaction are not dependent on one another. Are not dependent upon one another. In contrary to the Michaelis-Menten assumption that the enzymatic reverse reactions may be neglected, many enzymatic reactions are reversible. Previously, I have stated the fact that E plus S forming ES, and that is getting converted into E plus P. But the fact is, this reaction can only be applicable for Michaelis-Menten. But Halden equation has stated something different. They are stating that E plus P can again be reconverted into ES as well. Can convert it into ES as well. So, in contrary with the Michaelis-Menten model assumption that enzymatic reverse reactions may be neglected, many enzymatic reactions are reversible. This is called as the Halden relationship. Very, very important. It can occur as statement. Graph হিসেবে নাও দিতে পারে, but for statement, this is very important. And this should be the overall approach regarding Halden relationship. Here, ES might just well be called as EP because this model does not specify the nature of the intermediate complex. So, for this aspect, Vmax can be K2 into ET as we have previously known, and VR max, F means forward and VR means K minus 1 into ET. For this, ES is getting converted into E plus P. So Vmax on one hand, if it is a forward reaction, typically Kcat, over here Kcat can be K2. Over here Kcat can be K2. So K2 into what? ET. If Vmax, if the reaction is reversible, then what is happening? K2 for forward and for reverse K minus 2. So K minus 2, that means K minus 1, like K minus 1 into ET. So both these aspects can be taken under consideration when it comes to Halden effect. I'm repeating myself, for Halden, E plus P can be reconverted into ES. That is what they are stating. So for ES getting converted into E plus P, we have K2 on one hand and K minus 2 on the other hand. So K2 for forward, Vmax forward is K2 into ET, total enzyme concentration. And for reverse, it is K1. For reverse, it is K minus 1. K minus 1 into total enzyme concentration. So A equivalent should be as product concentration into substrate concentration, or V forward into Kpm and V reverse into Ks. So Km equals to what we have understood, K minus 1 plus K2 by K1. This is the Km. So that is by plotting it over here, k minus 1 plus k2 by k minus 2 and k minus 1 by k2 plus k1. This is a pretty unique concept, but most of the cases you will observe questions from this segment regarding the statement, not the mathematical formulation. So no need to dive deep into the mathematical formulations, but still, if someone asks about Vmax for forward and reverse, you can definitely analyze it from the overall reaction. That forward is, we are quite clear that K2 into ET was, it is a forward reaction, and for reverse it is K minus 1, as it is the initial state and is the reversible form, into total enzyme concentration. This should be sufficient for CSIR-NET as well as DBT, both. Now coming to inhibition. Coming to inhibition. For the theoretical approach, these are very, very important. Mark on the samples of inhibition. For part B, very, very important. On which pathway it is creating the inhibition, that should be understood, and on what are the texture or what type of inhibition it is conducting, whether competitive or uncompetitive or mixed. Now let's derive. So suppose in competitive inhibition, what is happening? Let's see. We have our enzyme and substrate, ES complex E to P. With the enzyme, as it is a competitive inhibition, that means the inhibitor is undergoing competition with with S, so that it can bind with E. As a result, we are getting another product called EI, enzyme inhibitor complex. So for EI, EI should be E into I by EI, as simple as that. And another thing we should be considering is what is the value of alpha. This is very important. What is the value of alpha? These two things are very important. Rate of inhibition, how inhibition is taking place. So the most important thing that can come from these kinds of questions is they will state you this kind of a graph, and they can either ask the value of alpha or ki or km, anything they wish to, and we have to understand this graph properly so that we can answer those questions. This is the main idea over here. So let's first analyze. See, for competitive inhibition, I have derived it, but no need to go into the derivation. E plus S, we have ES, from that E plus P. And as inhibitor, we have EI. It is undergoing competition. If someone is interested, let me know. I will provide you with the PDF format of this derivation. For now, let's assume, we have two things. One, we have the value of Ki, which is E into I by EI. Another thing is alpha, which is 1 plus I by Ki. These two things are very important. So finally, what we are getting? Finally, the product This is the final output of competitive inhibition. Now, if we closely observe the graph, let's see. From this graph, what we can interpret? First thing from this graph, over here, our Km, is increasing, and over here, our Vmax is constant. So this is the condition. Km is increasing and Vmax is constant. How can you understand Vmax is constant? Let's see this point. All of them, all the y-axis intercept are from a common point. All the y-axis intercept are originating from the common point. That's why Vmax is constant over here. And Km is increasing. How come? Let's see. When there is no inhibition, that means from the previous concept, slope is Km by Vmax. Slope is Km by Vmax. As simple as that. Now Km by Vmax, that means this is the slope. Now, if this comes over here, then this is minus 1 by Km. This is minus 1 by Km. Now, inhibition has increased. That means Km is increasing. And previously, what we have understood, when Km is increasing, that means the enzyme substrate complex formation will not occur readily. And as a result, product won't be synthesized as simply as the previous case. I'm repeating myself. The value of Km is increasing. That means enzyme and substrate won't be able to bind with each other because of the inhibitor. And as a result, product synthesis will be a bit late. Product synthesis will not occur properly. Km value raises. That means enzyme has least affinity towards substrate. Over here, they are not talking about affinity. Over here, inhibitor is there. So inhibitor is undergoing competition with the substrate to bind with the enzyme. As a result, enzyme and substrate are not be able to interact with each other. And as they are not interact with each other, production will be low. So value of Km is increasing when there lies a competitive inhibition. Value of Km is increasing. When the value of Km is increasing, product production will be less. Means minus 1 by Km, minus 1 by alpha Km. Suppose alpha 2. That means for this is 2 Km. And for this, it is minus 1 by 3 Km. So this is the overall approach. This is the overall reaction of Km. These are the x-axis intercept and these are the y-axis intercept. So as the y-axis intercept is originating from a single point, that means Vmax is constant over here. And as our x-axis intercept shows 3 distinct points, and if we consider it as 0 and the extreme point as negative, then minus 1 by Km for alpha equals to 1, alpha means inhibition, minus Km by, minus 1 by 2 Km, that means alpha equals to 2, that means coming close towards 0. Just like this. Originating from a single point, that means Vmax is constant. Now, we all know slope is Km by Vmax. Slope transforms into alpha into Km by Vmax. If alpha equals to 2, then 2 by Km. If alpha equals to 3, then 3 into Km by Vmax. This is the approach. This is the overall process. This is inhibitor. And as inhibitor is applied, what we are observing, the Km value is increasing. And as the Km value is increasing, enzyme and substrate won't be able to bind properly because of the presence of inhibitor. And as inhibitor is hampering this process, then product formation will be delayed. This is how the overall process of competitive inhibition works, where Vmax is constant and Km value is increasing. For competitive inhibition, Vmax is constant, Km value is increasing. As simple as that. If you wish, you can go for the derivation as well, but I think it's not necessary at this point. I have even mentioned if this overall graph can be represented in terms of our Michaelis-Menten equation, not in Lineweaver-Burk plot, then what will happen? This is the overall process. Sometimes question may even occur in this manner also, where on the x-axis we have V naught, on the y-axis we have substrate concentration. On the y-axis we have substrate concentration. So substrate concentration is Km when V equals to Vmax by 2. Substrate concentration is 2K when there is substrate concentration is K when alpha equals to 2. That means with inhibitor. That means, and simultaneously it can go on. And as the Km value will increase, the propensity for product formation will be decreased. Propensity for product formation will be decreased. I guess all of you must be aware, or I mean, must be getting the overall concept of competitive inhibition and how Km increase is hampering overall process of product formation and all. Now, our second approach is uncompetitive inhibition. Our second approach is uncompetitive inhibition. Now, in uncompetitive inhibition, what we are getting, we have our enzyme and substrate, and this enzyme substrate is forming ES, enzyme substrate complex. From there, enzyme plus product. Now, what it does, enzyme substrate inhibitor binds with the enzyme and substrate. That means there lies no probability of any kind of competition. It is not undergoing competition with that of enzymes. As a result, ESI is formed. And as ESI is formed, it will readily initiate the process of competition. So, unlike previous one, here we have KI dash, which is KI dash, which is ES into ES into I divided by ESI. For competitive inhibition, Ki should be E into I divided by EI. But alpha is 1 plus I by Ki. Here also alpha equals to 1 plus I by Ki. Inhibition. The binding of uncompetitive inhibitor, which need not resemble the substrate, is envisioned to cause structural distortion of the active site. Very important statement. Structural distortion of the active site. Statement wise question can come from this statement, thereby rendering the enzyme catalytically inactive. Structural distortion of active site of an enzyme. So we don't need to go for the derivation and all. Final, the product is like this. So y equals to m into x plus c. As simple as that. So in the y-axis we have 1 by v naught. On the x-axis we have 1 by s, just like the previous one. And our x-axis intercept y is equal to mx. Our x-axis intercept is minus alpha by km, alpha dash by km. Just like the previous case, how have we received it? Let's see. For x-axis intercept, y equals to 0. Therefore, y is equal to mx plus c, or if y is equal to 0, then x is equals to minus c by m. Over here, what is c? Alpha dash by m Vmax. Alpha dash by Vmax is our c, into what is our m? Our m is Km by Vmax, which gives us with Vmax by Km. Therefore, alpha dash by Km. So alpha dash by Km is our x-axis intercept. Similarly, by this calculation, we can also get our y-axis intercept. Y-axis intercept. So alpha dash by Km is our x-axis intercept. And for our y-axis intercept, that means x equals to 0. Therefore, y equals to c. And c is alpha dash by Vmax. This is our c. So our y-axis intercept is alpha dash by Vmax. Alpha dash by Vmax. 1 means 1 by Vmax. So Vmax over here is decreasing. 1 by Vmax is increasing, that means Vmax is decreasing. And on the other hand, minus alpha by Km, which is our y-axis intercept. As you can see, for 1 by Vmax, that means without inhibition, the value is 1 by Km minus. For inhibition 1.5, it can be 1.5 by Km. For this one, minus 2 by Km. So Vmax is decreasing and minus 1 by Km, is also decreasing in both the cases. So this is the overall approach when it comes to uncompetitive inhibition. My question will generally occur in this pattern. You have to analyze these segments or how we are calculating these things. Question must come from these, because in the question they will provide a graph something like this, and you have to analyze which point determines what. If you can derive that, then the entire problem is pretty easy. You can easily do it. So for uncompetitive inhibition, both Km and Vmax are decreased. For uncompetitive inhibition, both Km and Vmax are getting decreased. Lastly, coming to mixed inhibition. So over here, enzyme plus substrate, on one hand, EI, this is a kind of inhibition, whereas ES forming ESI as well. So inhibition is occurring in both the cases, in terms of ES, in terms of ESI. So competition and uncompetitive. So it is a combinatorial aspect of competitive plus uncompetitive. So K1, Ki should be EI and Ki dash both. So alpha and alpha dash, both the factors are introduced over here. Both the factors are introduced over here. May seem, there is a difference. It may seem like a typical competitive inhibition graph, but we must observe, the intercepts. We must observe the intercepts regarding x-axis as well as y-axis. That is how we can solve the problem. So final output is 1 by V naught. Final output is 1 by V naught equals to alpha into Km, alpha for competitive and alpha dash for uncompetitive. So our x-axis, x-axis should be 1 by substrate concentration, or y-axis should be what? 1 by V naught. Our x-axis intercept, x-axis intercept, that means y equals to 0. That means x equals to minus c by m. That means c over here is alpha dash by Vmax. Alpha dash by Vmax. And our m over here is alpha into Km by Vmax. Vmax alpha into Km equals to Vmax cancelled out, alpha divided by alpha into K. This is our x-axis intercept. Actually, when it comes to mixed, this kind of phenomenon will not occur. Let's see this graph. For mixed specifically, we have this and this. So therefore, our y-axis intercept, therefore x equals to 0, therefore y equals to c, and c is what? alpha dash by Vmax. So our y-axis intercept should be alpha dash by Vmax. Alpha dash equals to 1 equals to 2 होते पारे. Alpha dash by Vmax, where alpha dash equals to 1.5 possible, and alpha dash by Vmax, where alpha dash can be equivalent to 1. This is our y-axis intercept. So y equal axis intercept is alpha dash by Vmax. Coming to our x-axis intercept, that means y equals to 0. Therefore, x equals to minus c by m. Minus c by m means x equals to minus c by m. C over here is alpha dash by Vmax. Alpha dash by Vmax into m over here is what? M over here. This is y. So y-axis intercept, this one, alpha dash by Vmax. Coming to x-axis intercept, it's equals to minus c by m. C means this is y, this is m, this is x, this is c. So c is alpha dash by Vmax into m is Vmax on the numerator and alpha into Km. So therefore alpha dash by alpha into Km. So intercepts, alpha dash by Vmax, alpha dash by Vmax, alpha dash by Vmax. 3 intercepts over here also, alpha dash by alpha into Km, alpha dash by alpha into Km, alpha dash by alpha into Km. If this is 1, then this is 1 by alpha Km. If this is 2, then this is 2 by alpha Km. If this is 3, then 3 by alpha Km. So this is the overall approach when it comes to mixed inhibition. This is the overall approach when it comes to mixed inhibition. Very, very important. Specifically this derivation. First of all, I'm requesting all the aspirants to go for the basic graph regarding Lineweaver-Burk plot or Michaelis-Menten graph plot, where you can calculate at least the intercepts. If you are aware of the intercepts, then all these things are very easy and you can easily derive the problems. That can be done pretty easy. So for mixed inhibition, that's not the case. So this is the overall derivation. I will share if you wish to. So for non-competitive, you must see our Km is constant and Vmax is decreasing. For non-competitive, for uncompetitive, I'm just providing a brief overview. Yeah, this is what you should need regarding the overall analysis. When it comes to competitive, Vmax is constant, Km is increasing by a factor of alpha. Km increase. Therefore, enzyme and substrate binding, enzyme and substrate binding hindered, hindered. Therefore, least product formation. Pretty easy concept. Uncompetitive, Vmax is decreasing by a factor of alpha, and Km is also decreasing by a factor of alpha. Both are decreasing. When it comes to uncompetitive, when it comes to non-competitive, Km is constant. Km is constant, but Vmax is decreasing. So first, we have discussed about uncompetitive, then competitive, then mixed. Mixed is something different, not a non-competitive type. Mixed is where both the aspects are taken under consideration, ES and EI. And over there, a factorial Km is increasing, whereas Vmax is decreasing. Km is increasing, whereas Vmax is decreasing. Something like this is happening. So this is the overall approach. Another thing is, if these kinds of graphs are provided to you, just try to know these equations. That will help you to derive them. That will help you to derive them. Just try to analyze them. Nothing more than that. Okay, so the last thing we must know is, yeah, the basic formulas that we will need to solve any of these problems. V naught K2 into ES, V max K cat into ET, Km K minus 1 plus K2 by K1, Ks K minus 1 by K1, V naught we all know, V0, but this is very basic. Lineweaver-Burk plot. Another thing is Halden effect. Halden effect, pretty important, where E plus S, ES, this is also reversible. E plus P. So K1, K minus 1, K2, K minus 2. Both the aspects are taken under consideration. So therefore Vmax equals to K2 into ET when it is a forward reaction, and Vmax for reverse is K minus 1 into ET. This is Halden effect. Alpha is equal to 1 plus I by Ki, very important, and inhibition, very important. So these are the few things from where question come arise. I will provide you with the entire list of it. Last but not the least, this is very important. So for competitive, Vmax, alpha K, Vmax and alpha K. Vmax is constant and alpha K increasing. Uncompetitive inhibition, Vmax decreasing by a factor of alpha dash, and Km also decreasing by a factor of alpha dash. When it comes to mixed, Vmax is decreasing by a factor of alpha, whereas Km is also decreasing. Km is also, look, it's I cannot state it is decreasing actually. I mean, as both the inhibitions are taking place simultaneously, it will depend upon, as ES for mixed I am stating ES, E plus P. So E plus I forming EI and ES plus I forming ESI, and this kind of inhibition is also taking place. So there are multiple aspects that are taken under consideration when it mixed to mixed inhibition. So we cannot state if alpha is gradually increasing, alpha dash is gradually increasing, and alpha Km is constant, then definitely it will decrease. But if alpha Km is gradually increasing, is decreasing, then alpha Km will increase. So we cannot state the fact that in case of mixed inhibition, it is completely decreasing. And when it comes to non-competitive, inhibition, what is happening? Vmax is decreasing by a factor of alpha dash, whereas Km is constant over here. When it comes to non-competitive inhibition, Vmax is decreasing by a factor of alpha and Km is constant over here. So these are the four things that should be understood when it comes to inhibition and how they are actually working. I hope everyone is aware of it or got an idea about it. Last, yes. For final, AD-Hofstee plot. So this is the overall derivation. Better to state it as V0 by substrate S. Okay. So Y is equal to Mx plus C. On the x-axis, we are getting V0 by S, just like this. V0 by S on the x-axis. On the y-axis, we have V0, and the slope is Km. The slope is minus Km, as you can see. So from this, we can easily calculate our typical intercepts. So our x-axis intercept, that means y equals to 0. Therefore, x equals to minus C by M. Where is C? C is our Vmax, and M is our Km. So our x-axis intercept is Vmax by Km. Similarly, our y-axis intercept, that means x equals to 0. Therefore, y equals to C. C means we have our Vmax. So our y-axis intercept is Vmax. So this is how the overall AD-Hofstee plot is established. And this is the derivation of it from Michaelis-Menten equation. So we have to know how the Michaelis-Menten equation works, and from that the rest of the segments will come eventually. Now regarding AD-Hofstee also, we can analyze different aspects, like if Km increases, then what will happen, keeping Vmax constant. So there lies, regarding AD-Hofstee also, there lies certain conditions. Condition number 1, if Km is increased, Vmax is constant. First condition. If Km decreased, Vmax constant. Second condition. If Km constant, Vmax increased. So these three are main. Km increased, Vmax constant, competitive. Km decreased, Vmax constant. Km is decreased, Vmax is constant. No, sorry. Vmax also decreased. This is uncompetitive. Km is constant, Vmax is decreased. This is non-competitive. And there lies mixed also. So these kinds of inhibitions and graphical representations regarding these conditions can also be established, but that won't be necessary for DBT-BET examinations. In CSIR-NET also, I haven't seen something like this, but if you wish to know more about it or the mathematical formulations regarding it, then definitely comment regarding this. I will create another video where you can get an overall idea regarding this.